everyone, thank you so much for joining me for this video. Here are today's learning objectives. So the first is to understand reasons for the trends in melting and boiling temperatures, physical state at room temperature and electronegativity for group 7 elements. And then we're going to understand reasons for the trend in reactivity of group 7 elements down the group. And then lastly, we're going to understand the trend in reactivity of group 7 elements in terms of the redox reactions of chlorine, bromine and iodine with halide ions in aqueous solution, followed by the addition of an organic solvent. So now we're going to talk about group 7 elements, and these are called the halogens, and they're all nonmetals and exist as diatomic molecules. So for example, fluorine exists as F2, so it exists as 2 atoms of fluorine in one molecule. So there are particular things to know about each of these halogens. At room temperature, fluorine is a pale yellow gas, chlorine is a green gas, bromine is a red-brown liquid, and iodine is a black solid. So these are really important to remember because you can be asked about it, or when you're forming equations, sometimes you need stuff in their standard states. So for example, when you're doing questions about Hess's law maybe, and so you need to remember that fluorine and chlorine are gases, bromine is a liquid normally, and iodine is a solid. And so the trends we have for group 7 are that the atomic radii increases down the group. And this is because the number of electron shells increases. So for example, fluorine is in period 2. So its outer electron is in 2p5 compared to chlorine, which is in period 3. So its outermost electron is in 3p5. So it has that extra electron shell. And so the atomic radii increases. The second trend we have is that electronegativity decreases down the group. Electronegativity is the power of an atom to attract the electrons in the covalent bond, the pair of electrons in the covalent bond. And so because the atomic radii increases when we go down the group, that means there's more shielding, so the electrons in that covalent bond do not feel as big an attractive force from the positive nucleus compared to atoms which are further up the group. And then the third trend we have is for boiling points, and these increase going down the group because they're all non-metals, and because they get bigger, they have more electrons, and therefore they have more van der Waals forces, which makes them stronger. So they have stronger van der Waals forces between the molecules, and so more energy is needed to overcome them. And so the group 7 elements at the bottom have much higher boiling points compared to the ones at the top. And the reactivity of group 7 elements decreases down the group, and that's also because of the extra electron shells. So there's more shielding between the electron that it wants to gain to form a 1- ion and the positive nucleus. And so going down the group, it becomes harder and harder to gain an electron to form a 1- ion. And so that's why the reactivity decreases going down the group. Now we're going to have a look at chemical reactions of the halogens. So halogens usually react by gaining electrons to form 1- ions, and so are oxidizing agents. So for example, we have chlorine, and they normally form Cl- ions, and so they gain an electron, and so they are oxidizing agents because they are taking away an oxygen, because they are taking away an electron. And so that means that when they're trying to attract the electrons from the thing that it's oxidizing, it gets harder and harder going down the group because there's less of an attraction between the positive nucleus. So halogens react with metal halides in solution, and the halide in that compound will be displaced, which means replaced by a more reactive halogen. So for example, chlorine is higher up than bromine in group 7. So that means that it's a more reactive halogen compared to the halide, which is the bromide ion. And so when you put chlorine into a solution with the bromide, what happens is that the bromide is displaced. So the solution which is formed is now sodium chloride. And so the bromine is then formed. And we can tell if this occurs or not because bromine is red-brown. So it will have gone from being a colourless solution to a red-brown solution. And at the bottom, we have a table just to summarise what can be displaced and what can't be displaced. So the general rule is that if something is higher up in that group, then the oxidizing ability is bigger, and so that will be a more reactive halogen. So fluorine is more reactive than chlorine, and chlorine is more reactive than bromine. And so this is why fluorine can displace chloride ions, and it can displace bromide ions and iodide ions because it's the most reactive halogen. And then that's why chlorine can't displace fluoride ions because chlorine is one down in the group compared to fluorine, but it can displace bromide and iodide. And one really, really important note is that we can't investigate fluorine in an aqueous solution, and that's because it reacts with water. And one thing to note is that we can't investigate fluorine in an aqueous solution as it reacts with water. So following on from the displacement reactions, we're going to look at the colours. And so we've already learned that the more reactive halogen displaces the halide. And so we can see that for chlorine and chloride, there's no reaction to displace its own ion. Chlorine can displace bromide though. So for potassium bromide, the yellow solution of the chlorine has displaced the bromine. And but the chlorine can displace the bromide in potassium bromide, so a yellow solution forms. And then the chlorine can also displace the iodide, so a brown solution forms. And this is the same for bromine and chloride. So bromine and chloride, bromine can. So this is the same for bromine. Bromine can't displace chloride, and so there's no reaction, and the solution remains yellow. But it can displace iodide, and so that's why the brown solution forms here. And then for iodine, iodine can't displace any of them, and so there are no reactions for all three, and it remains as a brown solution because iodine is a brown solution. And then observations if we add an organic solvent are that for chlorine potassium chloride, it's colourless, so there's no reaction. And then for chlorine and potassium bromide, it turns yellow because the chlorine has displaced the bromide. And then for chlorine and potassium iodide, the chlorine has displaced the iodide, and so it becomes purple. And then for bromine and potassium chloride, there's no reaction because the bromine can't displace the chloride. And then bromine and bromide, there's no reaction, but it's the same. And bromine and iodide, the bromine can displace the iodide, and so it becomes purple because the bromine has displaced the iodide. And then for iodine and all of them, there is no reaction because it is the least reactive halogen. And the colour of the organic solvent layer in the test tube shows which free halogen is present in solution. So when we add an organic solvent, we get the free halogen present in the solution, and that's the colours that we see. And so that's why bromine is yellow and iodine is purple. And so you can see that all the colours in the table are either yellow or purple. It becomes chloride and bromine. And this is the same kind of logic